Hey folks, this is a short video about sine and cosine. So what we're going to do today is just define sine and cosine, which you've probably heard before, and talk a little bit about computing them. So the sine and cosine are defined in terms of the unit circle, which we introduced in a previous video. But just a reminder, it's the circle that's centered at the origin and has radius 1. So if we take another reminder, actually, is that an angle is in standard position if it has one ray along the positive x-axis, right? So its initial ray starts at the origin and points straight to the right along the x-axis. So if we put an angle in standard position, then its terminal ray, the other ray, is going to hit the unit circle somewhere. And we'll call this point the circle point of the angle. And sine and cosine are defined in terms of this circle point. We simply define cosine to be the x-coordinate of that point and sine to be the y-coordinate of that point. Now remember, an angle doesn't just have to be like 30 degrees or 45 degrees. We can have an angle of like 6,000, and that just means we wrap around the circle many times. We can have angles that are negative. That just means we wrap around the circle in a negative direction, in a clockwise direction. So this allows us to define cosine and sine of anything, and then we'll also define the tangent of the angle to be the quotient sine divided by cosine. And of course, we can only do this if the cosine's not 0, because you can't have 0 in a denominator. So tangent's not defined for some angles, right? If the cosine of an angle is 0. All of this is probably easiest to grasp using a picture, right? So here's a unit circle centered at the origin, and the radius is 1. That's the point 1.0, not 10. You can see it a little better at the top here, right? That's the point 1, the y value 1. So I have a circle of radius 1. I put my angle in standard position, which means its initial ray is along the positive x-axis, and then its terminal ray is, somewhere depending on where the angle is. That terminal ray hits the circle here at this black point, and then the coordinates of that point are the sine and cosine of the angle, right? So if I move my angle, let's make the angle a little smaller. So you can see the point rotates down the unit circle, and you'll notice as it does that, in fact, let's start with a really small angle way down here, right? So here, the x-coordinate of this point is almost 1. You can see it at the top there, the 0.999. And the y-coordinate is almost 0, right? 0.02 or so. And as the angle increases, right? So as I move the angle up, you can see the x-coordinate, it gets smaller, which is visually what's happening. And the y-coordinate gets bigger until I get to the very top of the circle, which I can do approximately there, right? And now I have an x-coordinate that's really small and a y-coordinate that's nearly 1. And of course, I can keep going indefinitely. I mean, my little gadget here can only go so far. But if I keep going here, right now, notice that the x-coordinates are negative because the point's on the left of the y-axis, and the y-coordinates are falling down from 1. So sine and cosine can take negative values depending on where this point is, right? If the point's over here in the second quadrant where the cursor is now, the x-coordinate will be negative and the y-coordinate will be positive. If it's down here in the third quadrant, both coordinates will be negative. If it's over here, the x-coordinate or the cosine will be positive, but the y-coordinate, the sine, will be negative. And in the first quadrant, both coordinates are positive. So this hopefully gives us a good visual understanding of what sine and cosine mean. It doesn't tell us exactly where these numbers are coming from, and we'll talk about that a little bit now. So first, some easy ones. First of all, because of the Pythagorean theorem, let's put this back in its original state here. Right, so cosine is the x-coordinate of the black point. That's the blue segment, right? The length of the blue segment is the x-coordinate, and sine is the y-coordinate. That's the purple segment, right? The vertical segment here. And those, of course, are legs of a right triangle. It's the triangle that you see in the picture. And so they satisfy the Pythagorean theorem, right? If I take the square of the blue side plus the square of the purple side, I get the square of the hypotenuse, which is the thin black side. Well, in our picture, the purple side is cosine theta, the blue side rather is cosine theta, the purple side is sine theta. So if I take the square of cosine theta plus the square of sine theta, I get the square of the hypotenuse, but the hypotenuse here is a radius of the unit circle, right? It's a distance from the center to the edge of the circle. And for the unit circle, that's just 1, and 1 squared is 1. And so I get this important equation relating sine and cosine. And this is true for any angle theta, right? Cosine squared plus sine squared is always 1, which means if you know one, then you automatically know the other because you can just use this equation to figure out the other one. Also, instead of writing cosine squared like this, which looks like the way you should write it, we'll usually write it like this, right? So this is what you'll see in books and stuff. That is, the square will come right after the cosine symbol and not around the entire thing. Probably a little better to use parentheses here. But again, that's not essential, just nice. Okay, so some easy examples of sine and cosine. First of all, if I take the angle 0, right? So the angle 0 corresponds to basically this right here, right? So an angle 0 means there's no opening whatsoever. And so the circle point is way over to the right on the unit circle at the 3 o'clock position. Well, that's just the point 1, 0. So the x coordinate's 1, the y coordinate is 0. So the cosine of 0 is 1. And the sine of 0 is 0, right? And again, that's because the circle point is 1, 0. And there are a few other points that we can do pretty easily, right? Those are the sort of compass points, north, south, east, and west. So north would be an angle of 90 degrees or pi over 2. So let's see. Right, there's an angle of pi over 2 radians or 90 degrees, right? We talked about angle measure in a previous video. And the circle point there is going to be 0, 1. And so the cosine will be 0 and the sine will be 1. And that's exactly, I think, what the next bullet says here, right? The cosine of pi over 2 is a right angle. So the circle point is at the 12 o'clock position. The x coordinate there is 0. The y coordinate there is 1, right? The circle point is 0, 1. And so we get the cosine and sine of pi over 2. So similarly, you can do the cosine and sine of pi, right? So pi is a 180 degree angle. It's the full circle, right? So there's the angle of pi. Circle point is -1, 0, right? It's over here on the extreme left of the unit circle. And so the cosine of pi is -1, and the sine of pi is 0, because again, the circle point is -1, 0. Cosine's the x coordinate, sine's the y coordinate. That's the key thing to remember. This is really the only idea we're going to introduce in this section, but it does take a little bit of practice to kind of get used to it. Okay, an exercise quickly before we move on and talk about some other angles, right? So we've talked about 0 and pi over 2 and pi. What about 45, pi over 4 and some other angles? We'll get to that, but a quick example first. Suppose that I have an angle and its cosine is equal to 5/8. Well, if the circle point's in the second quadrant, find sine theta. The key here is to use this Pythagorean identity, right? Cosine squared plus sine squared is equal to 1. And so if I know the cosine, right, so there's the identity. And if I know the cosine, I can plug that into that equation, right? I get 5/8 squared for cosine squared, and I can solve this for sine squared, right? So I just do a little math here, right? When I square 5/8, I square top and bottom, I get 25 over 64. I'll subtract it from both sides and then do 1 minus 25 over 64. And so sine squared is equal to that. And if I want the sine of the angle, which is what the question is asking us, then I should take the square root of both sides. And so I get the sine of theta is plus or minus the square root of this thing. And the last thing I need to do is figure out whether I want the plus square root or the minus square root. And to do this, I use the fact that theta is in the second quadrant. The second quadrant, remember the quadrants, this is the first quadrant on the upper right, and then this is the second, third, fourth, right? They're numbered in counterclockwise fashions. The second quadrant's over here. And in this quadrant where the cursor is moving around now, the y coordinates are positive, which means the sine value will be positive. That tells me that what I want is the positive square root, not the negative square root. I imagine this is what the next two items say. Yes, sine is positive, so we want the positive square root. And so that's our solution. Sine is the positive square root. And on my calculator, that comes out to about 0.78. Okay, let's talk about some other angles. We talked up here about the compass point angles, 0, pi over 2, pi, and so forth. What about pi over 4, which is a 45-degree angle? So here's a 45-degree angle, and I've put it in a triangle, and I've sort of suppressed the unit circle to keep the picture simple. Well, this is a right triangle, so this angle is 90, which means this has to be 45, and you may remember from geometry that this is what we call a 45, 45, 90 triangle. And in a 45, 45, 90 triangle, the sides have a very specific structure. The two legs are the same because it's an isosceles triangle. And then by the Pythagorean theorem, the hypotenuse has to be the square root of 2 times that side length. Okay, well, remember, this is in a unit circle, which means this black side, the hypotenuse, is equal to 1, and that allows us to figure out s, right? Square root of 2s is equal to 1. So I just solve for s by dividing both sides by the square root of 2, and I get this. Now, very often in books, what people do is they multiply top and bottom here by the square root of 2 so that the square root's not in the denominator. I don't think that's really necessary, so I don't really care whether you call this 1 over the square root of 2 or the square root of 2 over 2. Those are the same number. You'll often see the one that's in blue now, the square root of 2 over 2, when you're looking at books and websites and stuff like that. In any event, I know what s is, and notice that s is the length of the blue segment, which is the cosine of the angle, and the length of the purple segment, which is the sine of the angle. So now we know the cosine and sine of pi over 4. The cosine is root 2 over 2, or again, 1 over the square root of 2, either way. And the sine is the same, square root of 2 over 2, or again, 1 over the square root of 2. So yes, there we go. And whether you cite the angle in degrees or radians doesn't really matter. Notice also here that the tangent of pi over 4, remember tangent is pi divided by cosine. I'm sorry, tangent is cosine divided by sine, pardon me. And the cosine and the sine are the same here, right? And when you take a fraction where numerator and denominator are the same, you just get 1, right? So we're able to easily figure out the tangent of the angle as well. Okay, another sort of important triangle from geometry is a 30, 60, 90 triangle. So suppose that our angle down here is 30 degrees. Well, again, since this angle is 90 degrees, this means the one at the top has to be 60 degrees to make them add up to 180. So I have what's called a 30, 60, 90 triangle. And in a 30, 60, 90 triangle, the side lengths are in these ratios. That is, if the small side is called s, then the hypotenuse is 2 times s. And the longer side, the longer leg, is the square root of 3 times s. Again, that's sort of review from geometry, so I'll just kind of take that as known. That's something you probably did in geometry class in high school. In any event, once again, because the hypotenuse is the radius of a unit circle, it's equal to 1, which means s has to be 1/2, right? So I can quickly figure out s. And if I know s, then I know all the sides of this triangle, right? 2s equals 1, so s is equal to 1/2. And therefore, the cosine of 30 degrees, remember cosine is the blue segment, right, the x coordinate. So that is the square root of 3 times s, which is the square root of 3 times 1/2. And we'll usually write that a little more compactly as the square root of 3 over 2. The sine is the purple segment, and that's just s, which is 1/2, right? So the sine of 30 degrees is equal to 1/2. 30 degrees is pi over 6. That's something we talked about in the previous video, these equivalences between angle measures and degree measures. And so the cosine of pi over 6, square root of 3 over 2, sine of pi over 6 is 1/2. And again, we can figure out tangent without too much trouble here. Let's take the tangent of pi over 6. Oops, that didn't work. We'll just put that there. Right, so this should be cosine divided by sine. So let me make a little fraction here. And so the numerator should be this, and the denominator should be this. And what happens is the 2's cancel, right? So this just becomes the square root of 3. So I'll leave you to check that my math there worked out, but the tangent of pi over 6 comes out to the square root of 3. Again, the bottom line is, if you know any one of these, sine, cosine, or tangent, you can figure out the other two, right? If you know or I should say, if you know either sine or cosine, you can figure out the other two, right? Because if you know one of them, you can always use the Pythagorean identity to figure out the other one. And if you know sine and cosine, then you get tangent for free because it's just the ratio of the two. Okay, so what if, oh, this is where we were talking about a 30-degree angle. What if we rotate this triangle and put the big angle, the 60-degree angle, in sort of the spotlight down here at the lower left? Well, then the 30-degree angle, of course, moves up to the top. We have to adjust our side labels a little bit, right? S is the short side, so now that's down at the bottom. The hypotenuse is still 2s. The long side is the square root of 3s. Once again, s is 1/2, right? Because the hypotenuse is 2s, and that's equal to the radius of the circle, which is 1. The blue side is going to be the cosine. The purple side is going to be the sine. So we get the sine and cosine of 60 degrees from this picture, right? The cosine is just the blue side, that's s, which is 1/2. And the sine of the purple side, the sine is the purple side, which is the square root of 3 times 1/2, or the square root of 3 over 2. Right? And 60 degrees is pi over 3 from the previous videos on angles. So now we know that the cosine of pi over 3 is 1/2, and the sine of pi over 3 is the square root of 3 over 2. And of course, we could find the tangent just by taking the quotient of this divided by this. Okay, a few exercises here. So this is labeled from the notes and exercises, but you can see what we're trying to do here. Let's just find some sines and cosines. A cosine of 120 degrees. So how are we going to go about doing this, right? So the first thing I'm going to do is draw the circle point. And I think that's done down here. Let's see. Right? So here is a 120-degree angle, right? So 120 degrees means I go to 90 degrees, and then I go another 30 degrees, right? So this is roughly the triangle, and this triangle is called the reference triangle for the angle, right? So I draw the angle in standard position, and then I make this triangle using my two legs, right? So the blue side's the cosine, and the purple side is the sine. Right, this reference triangle now is a 30, 60, 90 triangle, right? Because this angle in here is 30 degrees because 120 is 90 plus another 30, which means this angle where the cursor is now is 60 degrees. So this angle must be 30 degrees. Okay, so because I have a 30, 60, 90 triangle, I know the short leg is 1/2 from what we were talking about up above. That's the length of the blue side. So that means the cosine of this angle is going to be -1/2. Notice that the x coordinates are negative in this quadrant. Excuse me. So the cosine is -1/2, and the sine is going to be the length of the purple segment. That length is going to be the square root of 3 over 2. Again, that's from the work we were just doing. And it's positive because I can see that the y coordinates in this quadrant are positive. So the sine of 120 degrees, whoops, is the square root of 3 over 2. Okay, what about this one? 2 pi over 3. So here I have an angle in radian measure. Again, a good first practice is to go ahead and draw a picture so you can see it. So let's go ahead and see if I can make this 2 pi over 3. 2 pi over 3 actually is the same as 120 degrees. So this is actually the same question that we just did. So let's just open all these up. Right, so that's what we notice. First of all, is if I convert this to degrees, and this isn't absolutely necessary. I don't suggest always converting from radians to degrees. It's easier just to kind of work straight from radians. But in this case, we notice that we've actually already done this. So we don't have to do the same thing again, and we get the same results. Okay, all right, so that was sort of a silly example, but no big deal. Let's move on and try to find this cosine and this sine of 3 pi over 4. So again, here, I'm just going to keep it in radian mode. 3 pi over 4 is 3/4 of pi, right? So pi is a straight angle, 180 degrees. So this is 3/4 of that, right? So here's pi over 2, 1/2 pi, here's 3/4 pi, there's my circle point. So this triangle is a 45, 45, 90 triangle, right? Because I've got a 45 degree angle here, which means these sides are both going to have length square root of 2 over 2. And I can see that in this quadrant, the cosine is negative and the sine is positive. So I've just talked through kind of the entire solution here, right? The reference triangle, which is this picture, is 45, 45, 90. Each leg has length root 2 over 2. And I just need to get the sines, SIGN, correct for cosine and sine, right? The cosine, the x coordinate here is clearly negative. So the cosine of 3 pi over 4 is minus root 2 over 2. And the sine is the y coordinate is positive. So that's going to be plus root 2 over 2. Okay, let's talk a little about angles in non-unit circles and then do another example, and I think we'll be good. If we put an angle in a circle of radius r, so not necessarily a unit circle, but some other circle, here's what the picture looks like, right? So here's my angle down here. And I have drawn in this dashed circle is my circle of radius r. So I'm imagining it is bigger than the unit circle. In my picture, r is 3, but it doesn't really matter. And here's the unit circle down here, this dashed circle, right, which has radius 1. I've drawn in the reference triangle, and I've also drawn in this kind of bigger triangle here. This is the point that the angle's terminal ray hits on the big circle up where the cursor is now. And these two triangles are similar triangles from geometry. All of their angles are equal. And because they are similar triangles, I can set up some side ratios. Right? In particular, if I do horizontal side divided by hypotenuse for each triangle, in the little triangle, the horizontal sides, the blue segment is the cosine, the hypotenuse is 1, the radius of the unit circle. In the big triangle, horizontal side is the x coordinate of the point, and the hypotenuse is r. And so I get this equation, cosine theta equals x over r. And if I do the same thing with the vertical side and the hypotenuse, so I take vertical side divided by hypotenuse, in the little triangle, that's sine theta divided by r, and in the big triangle, it's y divided by r. So I get these two equations, and of course, cosine theta over 1 is just cosine theta, and sine theta over 1 is just sine theta, so I can simplify that a little bit. And if I multiply both sides by r, I get a useful equation for the coordinates of the point on any circle that is kind of hit by an angle of theta. Okay, so here is an example. Let's try to find the coordinates of a point on a circle of radius 30 centered at the origin that determines an angle of 1.1 radians. So our picture is something like this, except now the big circle has a radius of 30, and this angle is 1.1 radians. Well, I don't have to do too much because I have these formulas, right? X is r cosine theta and y is r sine theta. So that means x is 30 times the cosine of 1.1. And I'll take this opportunity to point out that your calculator surely has a cosine and a sine button. So if you have the cosine or sine of sort of an awkward angle, not pi over 6 or pi over 4 or something like that, you can do it on your calculator. And my calculator says that the x value here is 13.61. And similarly, the y value is just r sine theta. So that's 30 sine of 1.1. And I can do that on my calculator, and I come out with that number. Okay, this example, yeah, I don't think I wanted to do that, that example, but I do want to do one other example here, one or two. Let's try to find the cosine of my fraction here, 14 over 3. I'm going, before we even do this, let's do 7 pi over 3. Right, so let's try to figure out this. So the first thing to realize here is that 7 pi over 3, this is 2 1/3 pi, right? 7/3 is 2 1/3. And 2 pi is one complete revolution around the circle, right? So an angle of 7 pi over 3 represents one complete revolution around the unit circle right? So that is 2 pi. Plus an additional rotation of pi over 3. Let me get my fraction back in, or we can just use this. And what this means is that this angle, 7 pi over 3, has the same circle point as pi over 3. Right? Because if an angle is sort of too big in a sense, that is, it's bigger than 2 pi, then when you make this picture from, a picture like this, what you wind up doing is going all the way around the circle, and then you just go around the circle again, right? So there's lots of angles that have the same circle point. 7 pi over 3 has the same circle point as pi over 3. If we went another 2 pi, that would take us to 13 pi over 3. That also has the same circle point, right? So does, we could just say 13 pi over 3. Right, and if we added another 2 pi, that would get us to, 19 pi over 3. Right, and on and on and on. There are lots of angles that have the same circle point. And if you have the same circle point, you have the same sine and cosine, because sine and cosine are the coordinates of the circle point. So this cosine of 7 pi over 3 is the same as the cosine of just pi over 3. Right, sine and cosine are what are called periodic functions. We'll talk more about this later on, but they repeat themselves. And so there's lots of angles that have the same cosine because they have the same circle point. So the cosine of pi over 3 is 1/2. That's from work we did up above. And so we have the cosine. Similarly, if I want to find, let's do one more and that'll be good for today. Let's try to find the sine of say negative 21 pi, right? So first of all, this is a negative angle. It just means that it's a clockwise rotation around the unit circle instead of a counterclockwise notation. I want to figure out kind of how many pi's this is. So 21 over 4 is, let's see, that's 5 1/4. So 2 pi is once around the unit circle. So an angle of this much represents 2 complete clockwise revolutions, right? So that would be negative 4 pi. Right, if I go twice around the circle. And if I express that in fourths, negative 4 pi is negative 16 pi over 4. Okay, so I have negative 5 pi over 4, right? So plus additional rotation of negative 5 pi over 4. So that means that this angle and this angle have the same circle point, which means they have the same sine and cosine. So if I want to find the sine of this, it's the same as the sine of negative 5 pi over 4. And 5 pi over 4, so that's negative 1 1/4 pi. So in terms of rotation, I would start here, rotate pi as 180, then go another pi over 4, and it would be exactly here. It would have this circle point. And so since this is a pi over 4 angle in this reference triangle, it means the side lengths are both 1 over square root of 2. I can see the cosine is negative and the sine is positive. So the sine value I want here is just 1 over the square root of 2, or I'll keep writing it square root of 2 over 2 for consistency. Okay, and that's the solution that we wanted. All right, that's a good introduction to the definition of sine and cosine. Take good care of yourselves, folks.